In this video, I'm going to do a teardown of this cheap third-party Raspberry Pi camera. I'll take a close-up look at this camera's image sensor. I'm also going to do a speed run to attempt to build as many optical systems as I can, using the exposed image sensor of this camera. Some of my attempts will succeed, while others will fail. Okay, so here's what the camera looks like up close. It's just a simple square PCB with a ribbon cable attached, and as I showed in some other videos, you can separate what you see here and do 3 different components. And here is what it looks like on the back side. And if you want to remove or replace the ribbon cable, you can do that by pulling up the black part at the top here. And to remove the camera sensor, there's a little lip here that you can pull up on, and it should just pop off of the connector. So I'll just put the tweezers under here and then pull up like that, and it just pops right off. Okay, and those are the pieces that we've got so far, and here's a look at the other side of those. So the actual camera sensor itself is inside of this piece, so I'll be taking this apart to see if I can get a better look at what the sensor looks like. Here's an even closer view of the sensor. As you can probably tell, it looks like it's a bit scratched up. That's because I've actually unscrewed the lens on this camera before. Even though it's not really designed for it, you can actually change the focus of these cameras by screwing the lens in or out a little bit. Alright, let's try to get this lens off again. Alright, I think I got it. Okay, here is a slightly better view of the exposed camera sensor with the lens removed. Down in the bottom left corner I put a dime to show the scale. So this right here that I'm poking is the lens. The lens focuses the incoming light directly onto the silicon sensor that you can see here in a purplish color. And hopefully, if things go well, we can get an even closer look at the sensor here. Here is a close-up view of the front of the printed circuit board of the Raspberry Pi camera. This here connector, that's where the camera sensor itself actually attaches to the printed circuit board. And here is a close-up view of the back of the printed circuit board. And here is a closer view of the front of the camera lens that we screwed out. And here is what that same lens looks like when it's flipped over. The separation between each of those lines is about 0.5 millimeter. So the total width of the screen here is 6 millimeters. And moving that up to the lens, which basically covers the full screen, that looks to be about 6 millimeters in diameter. It's a bit hard to tell because of the focal plane, so if I go up a bit, and that still takes the full screen, so I'd say that's pretty close to 6 millimeters. I would say at least 5.75. Here is a close-up view of the threads on this lens. So if I just go into focus on the grid, so each of the squares on that grid measures about 1/10 of a millimeter on each side. So I would say the distance between the threads is no more than 4 of those squares and no less than 3 of those squares. So I found at least one source online that said that the thread for these cameras is M6 with a pitch of 0.35, and that seems to be pretty consistent with what we see here. And here is the part we've all been waiting for. This is a close-up view of the camera sensor itself. So this is the actual slab of silicon that the image is projected onto by the lens. And that's a bit hard to see, so if I shine a flashlight directly down in there, you can start to see what looks like some of the bond points along the edge. And you can see that square region in the center, and I presume that is what is actually sensing the photons. And for completeness, here is a close-up view of the part of the sensor that connects to the printed circuit board. Now, before I try and take this apart even further, I'll probably try and get one more closer view of it, just in case I damage it. Okay, that shows a little bit more detail, but the illumination is pretty difficult. I'm actually holding flashlights right now in order to be able to see anything, so. Alright, behold, the Raspberry Pi camera sensor in all of its glory. I was fortunate that I was able to get that plastic piece on the side off of the top so that I can image it better. For reference, that plastic bit that you see on the right-hand side, that was basically glued to the top of the sensor, and it's also the piece that the lens screws into. The top piece that holds the lens and the actual silicon sensor seem to be bonded together with some bit of plastic or glue or something like that. The way I got those two pieces apart was by putting them in a really small vise but I made sure to put the top plastic piece in the vise while leaving the actual sensor just below it. So when I tightened the vise, it would squeeze the top part and break the plastic bond, and the silicon crystal on the bottom would not feel any of the stress. So in this case, it looks like that worked. Okay, here's a slightly more zoomed in view. This view is taken with the 4x microscope objective, and it looks like down around the edges you can see a bit of detail within the chip itself. Those little square things along the edges look like the bond points. And it looks like you can see some of the bond wires that are attaching the bond points directly to the connector cable there. So we'll just zoom in here to get a closer look at those details. Alright, we're starting to see some of the structure inside the chip. There's a thin coating on top of the chip, so that obscures some of the details underneath of it. It is really difficult to get the lighting right. I have to shine this flashlight at just the right angle to see those features. Otherwise they just go away. Let's take a look at some of the details on the other side of this chip. So I'm not exactly sure what that structure is on the side, but I assume it's things like buffers and amplifiers. Now that green blob in the center of the screen, that is the image sensor, and I can't tell if it's my imagination or if it's maybe just some noise, but I think I can almost make out the Bayer pattern on the image sensor. So now that I'm editing and I can zoom in and increase the contrast, I do think that I can see some of the structure within the image sensor itself. There's an interesting pattern. I'm not quite sure what that is. Here's what the corner of the chip looks like. So here is the Bayer image sensor. So while I was taking pictures of the Bayer image sensor, I was actually pretty rough with it. On a few occasions I touched it directly on the surface. I was also uncertain of whether putting it in the vise may have damaged it, so I thought this would be a great opportunity to put it back on the PCB and see if it still works. It turns out that it does still work, so I thought this would be a great opportunity to do a speed run and try and build as many optical systems as I can with absolutely no preparation. As you can probably imagine, there's a lot of engineering that goes into a sophisticated camera, but you might be surprised to learn that you can get a surprisingly good image by just taking a bare camera image sensor and holding it behind a lens at exactly the right position. Some of the things I'm going to try won't work at all, but a few of them give fairly impressive results. I figured I'd include everything and add some commentary. These cheap Raspberry Pi cameras give you a very affordable way to do experimentation with optics. So right now I've got the Raspberry Pi set up with the extra long ribbon cable, and I have a live video feed streaming from the Raspberry Pi to the laptop you see there. There's a delay in the streaming video feed of about a second or two, but it's still manageable for understanding what's going on. So here I'm showing a 4x microscope objective that has a couple adapters to attach it to basically just a couple of pieces of metal. I think the focal length for this objective is about 160 millimeters, which is approximately the length of that tube. So as you can see here, I'm using the highly sophisticated and precise optical method of taking a piece of Scotch tape and taping the exposed camera sensor directly to that open barrel. Now, as you can see, there's tons of light pollution coming in around the back of that, so it's not sealed at all. And the effect that we'll have will be to give a bit of a washout effect to the image. I can kind of reduce that effect by putting my hand over the back of it to hopefully make it a bit darker, and hopefully make it so that most of the light that's actually captured by the image sensor is the light coming in through the aperture of the objective rather than stuff coming in through the back. And surprisingly, you can actually get a pretty meaningful image out of that. So right now I'm looking at the Raspberry Pi logo itself on the board, so that'll give you an idea of the scale here. The Raspberry Pi camera sensor itself is fairly small in area, so you can imagine that most of the light that's coming in through the lens or the objective is actually getting wasted because it's falling on either side of the image sensor. The result is that it looks like you're seeing very, very high magnification, but in reality you're just getting the same magnification of the objective. The total available image that you could have with that objective is a lot larger. But since the Raspberry Pi camera sensor is so small, you're getting a very cropped version of that otherwise very large image. And right now I'm taking the Raspberry Pi camera sensor and putting it directly up to a magnifying glass. I was not able to get a focal plane with that. So here is a cheap monocular telescope thing that I bought from eBay. This is something I keep on my desk and use it to look at objects off in the distance every now and then. As you can see, I was able to get a pretty good image just by taking the sensor and taping it to the back of the eyepiece. In this case, light pollution from the back didn't seem to be a big problem. And here I have another cheap Soviet-era lens that I bought from eBay. Now for this, I was never really able to get a perfectly in-focus image. I tried putting another adapter in there kind of loosely between the lens and the sensor just to try and get it back a bit further from the lens. As you can see, it looks like it was almost in focus, but not quite. I think I had to pull it back a bit, but the problem was when I pulled the sensor back, then I end up letting in more light pollution from around the sides. If you're doing any rough prototyping like I am, you can think about the image that you see on the screen in terms of the sum of two components. Both of these components are added together to give you an image that possibly looks like complete blurry nonsense. If the image sensor is located at the image plane, then this component will be a nice in-focus image. If it's somewhere else, you might get a slightly out-of-focus image, but you can probably still make out some structure. This will tell you that you're close to the image plane, and you might be close to getting it to work. The second component of the light is from light pollution around the sides. If the optical system is well sealed and there's no reflections or glare or anything like that, then this component will be zero. But if you're just prototyping things like I am, and you have lots of light pollution from the back, you'll end up with the blurry looking convolution that you see on the screen throughout most of this video. So here I'm playing around with another little thing I bought on eBay. It's basically just a device with a narrow slit in it and a diffraction grating. The idea is that you can take incoming light and split it up into a spectrum. My thought process on this was to use it for some Raspberry Pi spectroscopy. In fact, there's another YouTube channel called Les's Lab that has a number of videos that demonstrates exactly this topic. In his videos, he shows how to achieve a very high quality result that's much better than what I show here. When you watch someone who knows what they're doing, they can make it look very easy. But in my video here, you can see that it's not quite that easy to get everything aligned properly. I struggled for quite a while to get the sensor in exactly the right position. And around here, you can see that I did get the spectrum to appear on the screen, but it was totally out of focus. Technically, this still does give you some information, but if your spectrum is out of focus, then you're going to lose a lot of spectral resolution, so you won't be able to clearly identify sharp peaks in the spectrum, and everything will just be spread out in blobs. The other issue here is that the spectrum was being spread out too wide, so the entire spectrum was being spread out so much that it couldn't even fit on the entire camera sensor. So here I have an achromatic doublet lens that I bought off eBay for 20 bucks. It was labeled as being for a telescope, so I thought, why don't I take a poster mailer tube and find a way to stick that lens into the end of it and try to make a telescope. So I took a cardboard box and I cut out a hole in it, and then I jammed that lens into it. So this was just a rough prototype, and I took some Scotch tape and put it right over the front of the lens. Alright, so here's my telescope. So this was my attempt at speedrunning a telescope, and halfway through I ran out of Scotch tape, so I had to find some packing tape, and I just used some Scotch tape to suspend the camera sensor at a point where I could kind of visually see the focal plane. And while I was doing this, it was kind of falling apart on me. And to fix the camera in there, I just suspended it with some tape near the end of the tube. Throughout this process, I found it actually quite difficult to get the camera sensor pointed directly to the lens. And I tried looking at a bunch of different objects at different distances, and I was never able to get a focal plane. And the cropping of the sensor and the exact angle of incident light just made it too complicated. And here I'm just trying to see what kind of image I can see through, it's a little like jeweler's magnifying glass that I keep on my desk for looking at small stuff. So I was never able to identify a focal plane out of that. This here is a 0.3 times focal reducer lens for a microscope. I think this is basically the equivalent of what you'd call a speed booster or a focal reducer lens for something like a DSLR camera. It basically just takes in incoming light and then focuses it down to a smaller point. Now it took me quite a while to get the Raspberry Pi camera sensor at exactly the right position so that it was actually looking through the eyepiece. So you can see here I'm struggling quite a bit to get the camera sensor at exactly the right position on the eyepiece so I can actually see through it. But eventually I did. So as you can see, I'm clearly able to get some focal planes out of it. So that one was a success. So here I'm just messing around putting a diffraction grating in front of the sensor just to see what happens. Nothing particularly interesting. And here I tried putting a polarization filter in front of it. That didn't do anything interesting either. Here is just another magnifying glass lens, although this one is a doublet lens. I messed around with that for a while and didn't get a focal plane out of that either. And here's an acrylic lens that I used for focusing some LED lights. I didn't have high expectations for this lens, but I figured I'd give it a try. And I didn't get anything interesting out of that one. I did see a bit of structure there, but I think that was just internal reflections from the lens. Okay, so the lesson here is that you don't need a PhD in optics to build an optical system. Sometimes you can just take a camera sensor and put it up to the back of an eyepiece, and you can see stuff. In other cases, things are a lot more difficult. I think this is especially true in situations where the focal plane is very narrow. So if you're doing something like a high magnification microscope or a high magnification telescope, then you're going to have to work a lot harder on getting the positioning right. The fact that the Raspberry Pi camera sensor area is so small makes it even more challenging. If you do get close to the image plane, you might not even recognize it because the image that you're looking at is so cropped. Okay, I think that's all I wanted to say. Hopefully that gives you some ideas on cool things to build with this $6 camera sensor.